Okay, welcome to Discrete Math Structures. This is lesson 2 on predicate logic. So what is predicate logic? It's also known as first order logic. Predicates are functions which return Boolean values. So oftentimes these are represented as part of a sentence. So here are a couple of examples of using some predicate logic. So here's a function right here. So p of x is going to be equal to x takes their umbrella, and r is equal to it is raining outside. So this first statement right here is our predicate, and this is just a proposition. So notice the difference between the two. A predicate takes in a variable, usually, some sort of parameters, and a proposition just stands on its own. So an example of an argument you could use using predicate logic is R implies P of X. So if it is raining outside, then X takes their umbrella, is how this would read in English. So predicates are useful in representing arguments symbolically. So sometimes we want to make statements about all elements of a given set. We can use quantifiers to represent such statements. So the existential quantifier is this backwards E, and we typically say that this is equivalent to there exists. And similarly, there's a universal quantifier, which is just an upside down A, and that's typically read as for all, or also like for any. That also works too. So those are our quantifiers. So here's an existential quantifier example. So recall that our predicate p of x equals x takes their umbrella. We can use the existential quantifier to state that there is at least one person who takes their umbrella. So there exists a person x such that x takes their umbrella. And we can also use this quantifier in mathematical statements. For example, this is read as there exists a natural number a such that a plus 1 is equal to 4. So here's our there exists a natural number a right here. So a in the natural numbers. That's what that E symbol represents. That's in, I guess. It can also be read as is an element of. And then there exists a natural number n, or a, such that a plus 1 is equal to 4. Note that this is true, it's just 3. But this is how this is translated from sort of a mathematical notation into like words. So here's an example of using the universal quantifier. So consider the predicate m of x is equal to x is a mammal. We can use the universal quantifier to state that if something in the forest is a human, then it is a mammal. So let h of x represent x is a human, and let f be the set of all things in a forest. So don't worry too much about sets, just think of it as like a collection of objects. So here's how we could represent something like this symbolically. So for all x in the forest, so for all elements in the forest, call them x, it's the case that if x is a human, then x is a mammal. So this translates directly into English as for all beings in the forest x, if x is a human, then x is a mammal. Now we can do things mathematically with this type of notation as well, which is typically what we're going to be using it for. So for all x in the real numbers, x times 0 is equivalent to 0, is how this reads, as you can see right down there. So sometimes we need to perform logical operation before a quantifier. So consider some arbitrary predicate p of x. Doesn't matter what it is. So if we're trying to say that it's not the case that there exists an x such that p of x is true, this is equivalent to saying that for all x, it is not the case that p of x is true. Similarly, if we want to do this with the universal quantifier, if we want to say that it's not the case that for all x, p of x is true, then we could say that there exists some x such that p of x is false. So we can do combinations of existential and universal quantifiers to make our arguments. So, for example, for all x in the real numbers, there exists a y in the real numbers such that x inverse is equal to y. So I think this also translates to for all x in the real numbers, there exists a real number y such that x inverse is equal to y. All right. So note that the order of the quantifiers matters. They're non-commutative. If we flip them in the example above, we would say that there exists some x for all the real numbers such that the inverse of x is y. So it's saying that there's one number that is equivalent to the inverse of all the numbers in the real numbers, and that's clearly not the case. So here's an example of some more high-order predicate statements. So consider the statement that x is odd, represented by O of x. So for all x in the integers, there exists some integer k in the integers, such that O of x, if and only if 2k plus 1 is equivalent to x. So for all x in the integers, there exists a k in the integers such that if x is odd, then it can be written as 2k plus 1. So that'll be very useful later on. And similarly, if we wanted to say something is even, then it would just be, x would be 2k. So for our next example, consider p of x to be the predicate stating that x is prime, and d of a and b, the predicate stating that a divides b. So in this example, we say that there exists a natural number p for all x greater than 1 in the natural numbers, such that if p is prime, then it's not the case that x divides p. And that's because p is prime, right? So there exists a natural number p such that for all natural numbers x greater than 1, if p is prime, then x does not divide p. All right? So that concludes this tutorial. In the next one, we'll be doing some stuff with proofs. So this will be applying this stuff. All right, thanks for watching.